Now I'm going to start one of the fundamental concepts in calculus. Sorry for the bad pun. The fundamental theorem of calculus. This theorem came up simultaneously in history with both Newton and Leibniz coming up with the basis of this. Now they worded it a little bit differently, but that's okay. They spoke different languages. Let's look at, before we get there, let's look at the relationship between differentiation and integration. It turns out that while we've kind of treated these like two separate subjects that aren't really related, they really are. If we look at the algebraic way of doing things, the non-calculus way, I could find the slope of a secant line, and the slope was, of course, delta y over delta x. While in calculus, we were looking at tangent lines, and in tangent lines, we could approximate the slope as delta y over delta x at any given point. Now, if you look at the area of a rectangle is delta x times delta y, while the area under a curve could be approximated by delta y times delta x. So it turns out that these two are related. They're very closely related. As a matter of fact, they're inverses of each other. Much like multiplication and division are inverses, addition and subtraction are inverses. And we've been kind of intuitively doing this without really doing it. Now, let's look at what the fundamental theorem calculus says. It says, suppose I have a function that's continuous on a closed interval from a to b, and I'm going to select, this is my general function here, and this is my a, and this is my b, and it's differentiable, and it's continuous, and so I'm in good shape. And it has an antiderivative on the closed interval. Then, this integral, or the area under the curve between a and b, is equal to the antiderivative at b minus the antiderivative evaluated at a. Now, this proof is, I'm going to be honest, it's a little on the slick side. All right? Let's assume we can partition this. And let's let this point right here be x naught, my a value, and this be xn. And so we're going to divide this up into different partitions. So if this is x naught, this is x1, x2, x to the n minus 1. So you see how we're dividing. See, we're doing these rectangle things again. I apologize for my diagrams here. All right, so we're going to partition it into rectangles, and this slate is much harder to use than you can imagine. So here's my little rectangle. Now, let me write f of b minus f of a in the following ways. F of b is really f evaluated at x of n. So that's f evaluated at xn. And over here I'm going to put minus f evaluated at a. And f evaluated at a is really f of x naught. All right? Now, you don't have any problem with my doing that. It's just a little space in the equation. But now, what if I keep adding 0? And by adding 0, I'm going to add a specific 0. So what if I subtract f of x of n minus 1, and then add it back, etc. And I'm going to keep doing that until I'm subtracting f at 1 and adding f at 1. Now, that's okay. I haven't done anything really weird yet. Let me rewrite this as a sum as I goes from 1 to n of the sum of f evaluated at x of I minus the function evaluated at xi minus 1. All right. Haven't done anything weird yet, have I? Now, by the mean value theorem, we know there's mean value theorem there exists a number c contained in the interval I, well actually in the ith interval, such that f prime at c sub I is equal to, well, let's go back to our definition, fxi minus fxi minus 1 divided by x sub I minus x sub I minus 1. Now, because I know that f prime at c sub I is equal to f at ci, I'm tired of writing all this out, so I'm just going to write delta I is equal to this x sub I minus x sub I minus 1. So delta I is just the difference there. All right, so I'm going to rewrite my FB minus A now. FB minus FA is the sum of I equals 1 to n of f c evaluated at I times delta xi. Now, this is a constant. And this constant is this Riemann sum. So now I'm going to take the limit as delta goes to 0 of this whole thing. And I wind up with FB minus FA, so the antiderivative evaluated at the endpoints is the integral from A to B, f of x dx. Kind of cool. Now, let's look at some guidelines for using the fundamental theorem of calculus. And by the way, mathematicians are the laziest people on the planet. We will abbreviate this FTC. So writing that on your paper after you have defined it once, particularly on an AP test, is fine. So if you can find the antiderivative, you can evaluate it. Now, this theorem doesn't tell you how to find the antiderivative. It just says it exists. And if you can find it, great. If we were to look at the formula, the integral from 1 to 3 of x cubed dx, we can evaluate it only by looking at the two endpoints. 3, this is my upper limit, and my lower limit. All right. You put in your upper limit, and then you subtract off your lower limit. You no longer need to include a constant of integration because this is a specific area. And it turns out, even if you try to add a constant, the constants wind up canceling. So don't do it. Now let's evaluate some definite integrals using the fundamental theorem of calculus. The integral from 1 to 2 of x squared minus 3x. Well, I'm just going to do this. This is x cubed over 3 minus 3x. Now I'm going to evaluate this. Now use this notation, evaluate it at 1 and 2. Now what I'm going to do now is I'm just going to plug this in. So this is 2 cubed divided by 3 minus 3 times 2. Now this is positive, and now we're going to subtract off 1 cubed divided by 3 minus 3 times 1. And now it's just a matter of doing a little algebra. You get 8/3 minus 6 minus 1/3 minus 3. And you get an answer of negative 2/3. So what this means is if I have the curve x squared minus 3, all right, let's see, 1x is 0, is negative 3. All right, if I were to integrate this function from 1 to 3, say this is 3 right here, okay, the area under my curve is negative 2/3. Now what does that negative sign mean? It just means that part of the curve is underneath the axis. That's all it means. Now let's look at 3 times the square root of x dx. Now, just because you have a constant here doesn't mean anything. Just pull it out. This is 3 times the integral from 1 to 4 of x to the 1/2 dx. So we can use our power rule. This is 3, x to 3/2 divided by 3/2, evaluated at 1 and 4. All right, so this becomes 2 times 4 to the 3 halves minus 1 to the 3 halves. And we get an answer of 14. So, what does this function look like? Square root of x looks kind of like this. From 1 to 4, this area is 14 units, whatever those units are. Kind of fun, isn't it? We thought this was going to be hard. What if I integrate from 0 to pi over 4 secant squared? Well, I know the integral of secant squared is tangent evaluated to 0 and pi over 4. So this is tan pi over 4 minus tan of 0. Now, I do recommend for the trig functions, I know you can look at this and go, oh, tan of 0 is 0. Go on and put in the angles, and then you can go on and mark it as 0, especially at first. So this is just 1. Think you can do a couple? Give them a go. When you're done, restart the video, because we are not quite finished. Now, what do you do if you're trying to integrate absolute value functions? Well, it's a challenge, but it's not that hard. You just take the function and break it up into its 2 components. I know the absolute value of 2x minus 1 is equal to minus 2x minus 1, my brackets here, and 2x minus 1, depending upon when this is positive and negative. Now, when x is less than 1/2, it's equal to minus 2x minus 1. And when x is greater than or equal to 1/2, it's equal to 2x plus 1. So you just take this and you break it from 0 to 1/2 of negative 2x minus 1 dx. And you add to that the integral from 1/2 to my final, which is 2, of 2x minus 1 dx. So you just break it up. All right, so this becomes minus 2x squared over 2, minus minus is plus 1x. We're going to evaluate it at 0 and 1/2, plus 2x squared over 2, minus x, evaluated at 2 and 1/2. Now you plug your numbers in. So this becomes minus 1/4 plus 1/2 minus 0 plus 0. Go on and put them in. Plus, that's 2 squared is 4, minus 2, minus 1/4 minus 1/2, and your answer is 5/2. Give it a go. See if you can get these. When you're done, turn the video on, back on. Now we're going to look at using the fundamental theory to find areas. We've kind of already touched on this. The area between x equals 0, x equals 2, and this curve is very straightforward, and x equals 0. All right, basically what we're going to do is we're just going to integrate this from 0 to 2. Now go on and make sure you do your sketch so you understand that you're doing this area right here. Okay, this becomes 2x squared over 3 minus 3x squared over 2 plus 2x evaluated at 0 and 2. So this is 2/3 times 2 squared plus 3/2. Oops, that's a 3, isn't it? That should be a 3. 3/2 times 2 squared plus 2 times 2 minus 0 minus 0 plus 0. And you get an answer of 10/3. All right, try this one. When you're done, turn off the video and have a good evening.